So for my project, I wanted to write a program that records my audio as I'm playing guitar, processes the audio to detect the key of the song. Once the key is determined, I wanted to then store that data in an array or a database where I can compare the keys of the songs. So I determined the songs by taking the list of the top 100 songs to learn on Ultimate Guitar Tabs, which is a popular website for guitarists to go and learn music. So their list of top 100 is the most commonly or most frequently looked up songs. So I felt that was a pretty accurate indication of what the most popular songs to learn on guitar would be. So initially, my plan was to use a third-party program called Abject Audio Inputs to achieve my objective here. As you can see, each frequency has its own key binding. I was going to take these key bindings as inputs and then just send that directly into my database where I can then compare the different notes. However, I was having issues where the software wasn't accurately picking up the notes, where I would play two different notes and it would determine it was the same. So I decided to scratch that idea and just make my own software to accomplish this task. So first thing I needed was a recorder program that takes input from my audio interface that I have and transforms it into a WAV file. So I'm going to go ahead and run this so I can show you how it functions. It tells you when it starts recording and gives you a countdown. In this example, I just did a quick 10-second clip to give you the idea, although in my actual program I use 15 seconds to get a better idea of the song. So from here, I'm going to switch over to my Google Colab sheet for the purpose of presenting. I uploaded an example of how I processed each song that I'm going to go through here. So first, I'm just going to start with the tools and libraries that I used to accomplish this. The language I used to write my entire program was Python, and although I am using the Google Colab sheet here to present my project, my entire program was actually written in VS Code. The libraries I used were PyAudio and Wave, and those two were to accomplish the recording and transformation of my audio file. I also used Matplotlib to graph my data. I used IPython for audio playback purposes. I use NumPy as it is necessary to use with the librosa library, which librosa is actually the library that's doing most of the heavy lifting in this project here. Librosa is the library I used to transform and record all of my data that I needed. So to give you a quick example of how this works, I loaded in an audio file, one of the 100 that I recorded, loaded that into librosa, and I'm using IPython here to play back that audio. So let me give you a quick sample of that. Right, okay, so that is the intro to Stairway to Heaven on guitar. And here, using the librosa display wave plot, is a wave plot of that audio recording, with the Y being a n-dimensional NumPy array of raw data, and SR being our sample rate. And a sample rate is how many samples the program takes per second. So the standard sample rate for librosa is 22,050 hertz. Of course, you can change that, although for our purposes, that works fine. Give me one moment here. So while the wave plot is pretty cool, and it is a format that I'm sure many of you have seen before, if you've ever worked with a DAW or a digital audio workstation, I'm sure you're familiar with the wave plot. However, this isn't going to get us the information we need to determine enough about the audio. We're going to have to transform this wave plot into what's called a spectrogram. So a spectrogram is a visual representation of the spectrum of frequencies of a signal and how it varies over time. So here we're going to be looking at the x-axis, which is time, and the y-axis, which is frequency. So in order to create the spectrogram, librosa actually has a function called short time Fourier transformation, which takes the raw data created earlier and gives us this image below. So this is just a short time Fourier transformation given the raw data that we created above. Okay, so this is a spectrogram. And as you can see, all of the action is happening here at the bottom of the spectrogram. So we can zoom in by transforming from a linear frequency map to a log frequency. This gives us a more focused view of our data, as you can see here. But we can still do better. librosa actually has a function called constant Q transform, which gives us an even higher spectral resolution at lower frequencies, giving us a better idea or indication of where frequencies and notes differ from each other, giving us a more accurate picture of what's being played without as much background noise. And here is the spectrogram using the constant Q transform. Now, we could have just started, given that it still only takes y and sample rate as an argument. We could have skipped the short time Fourier transformation altogether. The only reason I even included it in the sheet, just to give you guys an idea of what a spectrogram is and what our starting point is. Okay, but now that we have a clear image of what frequencies are being sounded at different times, we can collapse octaves into their respective chroma. Now, a chroma is the pitch class of a note. So, as you may have heard of, C4 has a frequency of approximately 261 hertz, right? And a C5 has an approximate frequency of 523 hertz. And even though these two have different frequencies, they are both in fact C. They belong to the same pitch class. And so we can create a chroma of the different pitch classes using librosa once again. It has a function to create a graphical representation of the chroma, shown here. I think this looks a little bit like a piano, so you can kind of start to see the music of it, right? It's starting to look like something we might recognize as music. The problem we face though now is that the frequencies are bleeding into each other. As you can see, it looks like multiple are being played at the same time. So the solution to this is to measure the note at the moment it is played. This gives us the most accurate depiction of the frequency. The beginning of the note is called an onset, and luckily librosa has yet another function to find the highest onset strength of each frequency. Here you can visualize where the onset strength is higher at the peaks of this graph. Now, using this onset, librosa can determine where each beat starts. Okay, so to give an audio representation of these beats, here they are in graphical form again, and here is librosa creating essentially a click track that predicts the tempo, uses nothing but the onset peaks to determine it. So we'll give this a quick listen. Let me turn this down before it's too loud. Right? So that is the same audio, just with librosa's click track that it made using our data over it. So this tool could potentially be used to measure the BPM or the tempo of a song. You know, that's something that would have been cool to implement in my program. However, unfortunately, when I recorded my audio tracks, I didn't play to a metronome, so it likely would have been inaccurate. However, using these beats that we just measured, along with our chroma, we can plug these into the librosa's display function again, and now we'll get a nice clear image of what notes are being played. As you can see, there's still multiple notes that appear to be playing at the same time. But that's actually because what we hear as one note is actually several different frequencies sounding off simultaneously. This creates one of the hardest problems to solve actually in audio engineering, and forced me to pivot my whole project. While it was my intent to measure every note in the audio file, I quickly learned without the help of deep learning that wasn't really going to be possible. However, I could reliably determine with the data that I do have the key signature of the song. Now, the key is most reliably found by two things, and that is how often the note is played and what the first note of the song is. So as long as I could find those two things, I could determine the key signature of the song. Now keep in mind, the data in librosa here is actually just a numpy array. So all we have to do is sort this array to determine what the most commonly occurring chroma is. And as long as it was somewhat accurate, we'll be able to reliably determine the key of the song. So I stored the results from my algorithm in a list. I followed this process for each of the 100 songs, and I graphed it. Here's the results. This is the most commonly used keys in the top 100 songs to learn on Ultimate Guitar tabs. So in first place, we have the key of G. In second place, the key of D. And tied for third, there's A and E. Now, of course, this doesn't take into consideration things like major and minor scales, but it does provide some idea of what keys make for a popular guitar lick. Now, the only question I needed to answer was how accurate is my program, right? So I recorded the actual keys of each song by hand, just using my knowledge of music theory. And with this, I was able to determine that my program was surprisingly accurate. Here's the graph displaying the actual key signatures of each of those songs. My program only miscategorized about 10 key signatures out of 100, giving me 90% accuracy. Additionally, the ones it miscategorized typically only a half step off. So half step would be from A to A sharp, or C to C sharp, and so on, right? And in addition to that, I mean, the method I use isn't 100% accurate. You can't reliably get the key signature just from the most played note. However, as you can see here, it is the case about 90% of the time. So, I just want to quickly go over some different points to make sure that I covered everything. What changed from the initial scope of my project is that I went from looking for all notes that I played in a song to just the key signature. Okay, and I also went from using third-party software to writing my own program. Some technical challenges I faced. It was quite a long list of technical challenges given the scope of my program here. However, the largest technical challenge that I ran into was the one of not being able to distinguish separate notes reliably. This is something I should have anticipated when the third-party program wasn't accurately doing it. However, after research, I found it's just not an easy task. But my biggest success was being able to determine the key signature 90% of the time. That is a big success point for me. However, my biggest failure, again, was not being able to record those notes individually. I was really hoping to be able to gather more information from the data I recorded, which actually leads me into my next point about doing the project over again. If I were to start from the beginning, I would actually like to pick something that gives me a bit more insight from the data I retrieved rather than just the key signatures of a song. If you're playing a song and you're familiar with music, you can determine without the help of a program what key signature you're in. But that's okay. You know, I'm still happy with how the program came out. But, you know, if I were to stick with the same idea, some things I would have liked to implement, like I said before, was an indicator of the tempo using the beats. All I would have needed to do for that really was play to a metronome, and I would have been able to also predict the most popular BPMs for the songs. Or something else that would have been cool is some kind of automation where there's an event listener listening to my audio interface that when I play, it automatically records a WAV file and sends it to this program. That's something I would have liked to implement. And while I already went over the tools, I just wanted to reiterate everything was built on Python. This isn't my actual program. This is just an example of a single audio file of how my program works. And then I used Visual Studio Code to write the rest of my program. And I would not have been able to do any of this without Librosa. That library has provided so many awesome tools that really made this doable. I wouldn't have even known where to start otherwise. But yeah, that's my project.